So now let's look at another very popular type of front, the so-called shelf break front. There are fronts that tend to form along the shelf break. And the reason why there are fronts forming is because the properties of shelf water can be different from the properties of the open ocean. We talked about that because of continental runoff, river runoff, and also enhanced heat fluxes. Okay? But the shelf break is a location where actually on one side you have relatively shallow water, and on the other side the total water depth increases. So what happens along the shelf break is if there are disturbances, the total height of the water, you actually stretch the water column, okay, or if you move it back, you compress it. And this does something on the longer time scales. This compression or stretching of the water column actually produces disturbances that move the water back towards the shelf break. It's to do with conservation of angular momentum in the ocean. But anyway, there's no need to go too much into the details, just telling you that the shelf breaks are special regions. Okay, shelf breaks are special regions. And here's one example of a shelf break front. This one is on the shelf of the mid-Atlantic Bight, taken south of Rhode Island. Okay, and here are measurements of temperature, salinity, and density. Vertical transects. Okay, so the y-axis is depth, and the horizontal axis is distance, horizontal distance, and the scale is 100 kilometers here. Let's have a look at the density. Okay, so you can see here on the right, let's activate the mouse. Density field. Okay, let's look at the colors. Okay, you have purple on the right, high density. Shelf water has a lower density, and you know that you have to add 1000, then you get the density in kilograms per cubic meter. This is sigma T. Okay, and you can see its contours are shown here, and you know that with contours you use a constant contour interval, and you can see where the region where you have more lines, there is a bigger horizontal change. So in this area here, you get a rapid change of density. Okay, you can see here that's a change of 5 units. Okay, there are 5 lines here horizontally. This is what we call a density font, and then you can apply all your knowledge. Swift horizontal flow, convergence, downwelling, strong turbulence. All right, so this is a shelf break, and the fisheries they know that. That's why they go to the shelf break. Popular fishing areas, the shelf. If you want to go to the shelf break with your grandma, so you're in your inflatable and it can be quite a distance. So if you want to go fishing on the shelf break, wow, hang on, you need to plan that a little bit better. Okay, so what actually makes up this density front? Okay, that's the next question. So just asking, is it temperature or salinity? Let's have a look at the salinity field, and the middle one. Salinity is, you look at the numbers here, colors can be misleading. So what is the red? Lower salinity on the shelf. Okay, lower salinity on the shelf? Oh yes, it's definitely to do with low salinity water. It's very, very likely a continental runoff, reducing the salinity in shelf. Okay? Well, that could explain that, but what about the temperature effect? Temperature effect on the left. Okay, you see here, it looks like warmer water. No, hang on. Hang on, be careful. Red, but look at the numbers. Cold. Cold water. 4 degrees, 8 degrees. Colors can be misleading. In this example, red colors, orange and yellow, actually refer to cold water. Temperature would on its own increase the density, but the salinity effect offsets the temperature effect. And so it's salinity that actually makes it low density water, light water on the shelf. Hooray! So this is just a reminder that you always need to take your time, study, have a look at these systems carefully, and don't make too quick conclusions. All right.